from Plymouth Marine Laboratory, and I suppose the first thing I should do is sort of give a bit of background on what I do and where we're sort of coming from with this project. So I'm a molecular microbiologist by trade. Sanitation is not a sort of field that sort of falls naturally into my domain. I sort of work on genomes and proteins and single genes, and that's sort of my background. I have tunnel vision, so that's what I do. So I'm here now for exposure to sort of open my eyes to this world. So 10 years ago I started work at Plymouth Marine Laboratory, and I thought it was pretty crude back then when I had to go from sort of yeast and E. coli, very controlled systems in small volumes, to working with seawater, which I considered a very crude media to work on, dealing at 1, 2, 3, 4, 5 litre scale of this really, really crude, wet matter that I thought it was. Now I found myself working with the sort of sludge area, and it's just a world of difference. So I'm going to tell you about our Vortex bioreactors and their application to the sanitation problems. So Vortex bioreactors is actually very, very simple. Vortex separators have been on the market for donkey's years now. So they're well-established machinery used in the sanitation industry already as dewatering devices, also used in the oil industry to separate oil from seawater and sand. So they're a proven technology, totally scalable as well. I mean, you can get different sort of size systems, ranging from 8,000 gallons per minute capability of processing down to very much smaller ones. And the actual rationale behind this is very, very simple. You basically have when I turn you can't hear me. You basically have a mixing area and a very intense sort of cyclone forms, and you use this separates out, and the lighter material goes towards the center, and you separate through a manifold. So that's just the sort of rationale behind them. Anyone who wants any sort of evidence of the sort of chaotic, turbulent, destructive force going on in these areas just needs to look on the news at the moment to see the effect of that at scale on the east coast of the USA. So what we're doing is basically containing a cyclone within a tube, just like this. So, like I said, I come from a marine background, and we're utilising this technology for biofuel production. What we intend to do is put algae in the air, break them apart, do the transesterification, and then a one-step isolation of lipids, which are lighter, down through a separation manifold. It's technically very, very challenging, and it'll keep you busy for the next 10 to 15 years, I think. A spin-off from that, quite literally, was when I had the idea that maybe we could put contaminated water in here and use this intense mixing zone, and forget about the separation properties, and just use this intense mixing to destroy cells. So we wrote a grant to the Gates Foundation. We were pretty naive at the time. We didn't really know much about the sanitation industry and what the real problems were. And we basically said we'd do everything. We'd develop a system which separates fecal matter from wastewater and at the same time reduces the activity and viability of pathogenic organisms in both fractions by continuous in-situ treatment with a low-cost formulation of biological and chemical agents, which was a pretty outstanding statement to make at the time. Fortunately, the Gates Foundation saw through our ignorance of the problems and gave us a chance. So we've been on quite a steep learning curve since then. And what we've done is we've had a slight change of emphasis now. We thought we'd solved one problem as opposed to all of the problems in one go. So where we've been focusing is on contaminated water, essentially, secondary effluent. What we envisage is our Vortex bioreactor can be used at this station here. So where you've got pathogen-rich water held in a tank, we can process it and sterilize it, and then this can be used for either sale or, at the very least, stop the discharge of this sort of heavily microbially contaminated water to a river. So that's where we are in our rationale. So we have quite a few of these systems. One thing I have to say about this technology is that's completely scalable. So even within our lab, we've been working on this sort of stuff for about 12, 18 months now. We have 5-litre systems all the way up to about 1-ton systems. And we're just playing around with these in our lab. So what you've got up here is one of our first early generation models, which is what we call the SP2. There are 3 pools involved in our project, in our lab. So for some strange reason, we decided to call our equipment after one of the pools that makes it. So as well as 3 human pools, we also have a load of sort of equipment called small pool, which is what the SP refers to. So SP2 is the 2nd generation of the small pool. It's about a 40-litre system, and we have various different configurations of this with separation chambers, closed loops, and small-scale things. And at the moment, we're running these with a drill that you can obtain from any sort of hardware shop. We can also do this by hand as well with a hand crank system. We also have a larger system as well. So when we first sort of came up with the idea of using vortices as reaction areas, we had to sort of obtain a vortex separator and then modify it to turn it into a vortex reactor. We started talking to a commercial company that makes these things. It was going to cost about $120,000 to buy a really nice vortex separator. We were going to buy the Ferrari of the vortex separator world. So we got into discussions with these guys about purchasing one of them. And all of our questions centered around sort of taking it apart and reverse engineering. And understandably, the company sort of got cold feet with selling us one, because basically we told them we were going to break it apart and remake it in our shape. So they stopped talking to us, so we had to sort of source a vortex separator from somewhere. So we actually found one on YouTube in the middle of America. And it's this one up here, called BD, after the guy who built it, Big Dan Drumheller. And we found it's got an outboard boat motor on it from his local boatyard that he picked up. And it's a propeller in a tube. And we saw this on YouTube, which he just put up there for a joke, really, and said, "We think that's the most amazing thing we've ever seen in your life. Will you sell it to us?" His response was really enthusiastic, and he basically said, "Yeah, sure, I'll have to find it first," because he'd taken it apart. So he sold it to us at a profit to himself for about $2,500. So we sort of saved ourselves about £100,000 by getting an American-built vortex separator. And then we basically stripped it out and sort of tried to sort of work out how these things were working and sort of start optimizing our things. Turns out that Dan Drumheller actually owns an engineering company, which he didn't tell us at the time. He turned into a really useful guy. So he's been building us loads of different versions of this. And now we're up to Big Dan 3.1, which has a bow thruster motor from a 400-foot yacht on it. It can turn a 400-foot yacht on a sixpence. And at the moment we can't use it because we can't feed it with enough water because it goes so quickly. But it's a really impressive sort of setup. This is where we were originally off this little outboard motor. So we have this capability at scale. That's the thing with our technologies. We envisage it being used at a single toilet scale, but it can also be used at the city scale as well. So the experiments I'm going to sort of show you the results for were done in what we call an SP2CL. The CL refers to the closed loop, so we're not worried about separation anymore. We're just using that propeller, which comes off a model boat and is available for about $5 online, and we've got it in a tube, which the tube is actually quite expensive because we wanted it clear so that we could look at it, because everyone likes to sort of see these things as they go around. But really, you could actually build this rig. If you weren't interested in seeing what it's doing inside, you'd probably build this for about $15, maybe $20. It's about an 8-litre working volume. And we've modelled, this is theoretical modelling, and we sort of modelled the swirl inside. You can see the air bubbles at the centre. So already the vortex is forming and the lighter material is going towards the centre. So, like I said earlier, we're doing this for biofuel production, so we really need to understand sort of separation and mixing properties within the tube. So we're quite fortunate in this project from the Gates sort of perspective that we're having a lot of support from our parallel projects which are utilising the technology for other purposes. So we have various sort of models that are coming online now. So on the left here you see the sort of flow measurements in the field of the direction of the pipe, and here we're going across the cross-section. And the interesting thing is that we were absolutely dismayed when we saw this for our biofuel production, because the swirling and the mixing weren't exactly what we wanted for separation properties. Because basically a model boat propeller is not designed to create a vortex. It's the opposite of what it's supposed to do. However, from a sanitation perspective, it's fantastic because it's drawing the water in and back, and there's actually a reverse flow here, and the intense mixing zone is really quite spectacular on this thing. And we were completely unaware of this until we started modelling this with lasers. We had beads in there, and we could see the beads moving through the tube, and we had no idea that it was actually a reverse flow. Occasionally we'd see a bead go backwards, but we sort of kind of ignored it because it sort of drew in what we were thinking. So we've been putting, like I said, we've been putting beads into the reactors. Essentially, if we rely on the intense mixing zone, nothing happens in terms of destruction of cells. So what we have to do is actually add an antibacterial agent into there. So to make this work in the real world, that agent will have to be fully recyclable and very robust. We've been playing with alginate over the last 3 to 4 months. You can make really pretty colours, and there's nothing quite like watching rainbow-coloured beads going around in the tube, round and round and round. It's really sad, it's very satisfying to look at. But ultimately, when you're running experiments, you have to have something that actually is sort of biologically active. And we've been using a lot of copper in our experiments. These are 4% copper alginate beads. So making these beads is quite difficult. It's very, very easy. It's very, very time consuming unless you've got a machine to do it. So I tasked my technician with finding a way of making these beads very, very efficiently. He's a Swiss guy, and he sort of first of all found an engineering company in Switzerland that could sell us a alginate bead maker for about $20,000. So I figured that was a bit of a useless, well, it's a poor use of resources. So I said, we'll go with the Swiss-made option, but you've got to get in the lab and do it yourself. So all of these beads have been made by hand with a needle syringe, drop it into calcium chloride. The poor guy, I asked him for a kilo of beads, which I would never actually use because you don't need that many. He spent 4 days making these. He was slightly heartbroken at the end, but he had a really strong thumb. So we sort of started off in shaken incubator flasks, testing sort of our active agent. We tried lots of different metals, nanoparticles, so we tried copper, lead, zinc, silver, silver nanoparticles that you get out of washing powders, surfactants, biocides, things like chlorhexidine, polyhexamethylene bicarbonate. We tried those as well as glass bubbles to make the alginate beads more buoyant and things like that. The results were outstandingly dull. I apologise for putting up these really small graphs, which are small for a reason, is that we were doing these as a quick look-see. I never expected to present these data. But what we did do, we sort of had a mass sort of screening program. About 4,000 agar plates and 50,000 colony counts later is a massive underestimation of how much work that the guys did in the team. It's probably closer to about 7,000 or 8,000 plates, which takes up an awful lot of space. It probably takes up about the number of agar plates we used in generating the data I'm describing today will probably take up the size of your bathroom in your hotel room. Fortunately, we had a walk-in fridge in the lab, so it wasn't too much of a problem. But after about 6,000 or 7,000 plates, we were ready to sort of upscale from 100 plastic scale and go into the Vortex bioreactor. So we were using this system, an SP2CL, and we were really sort of excited about it. We sort of liberated a device that we use in our photobioreactors in the Marine Lab, which measures oxygen, temperature, pH. So we had all these sort of probes and everything. The actual probes were worth far more than the actual rig, which was only worth a couple of $100. And we were really, really, really excited, and we sort of settled on 4% copper as our active agent. We knew in 100 mil flasks they worked really well. So we were absolutely mortified when we got this for our sort of death of E. coli. So at this point, we've been going for about 3 months, and this is our first experiment in a Vortex bioreactor. We actually had no kill of E. coli whatsoever. But then we looked at the oxygen data, and basically there was no oxygen in there after this point here, because we put a lid on there. So we just ran the experiment again and took the lid off, and the results were pretty outstanding, really. So when we inoculate the Vortex bioreactor with 1 million E. coli per milliliter, so you can see in the first half hour here that there is no active agent in the Vortex bioreactor. The E. coli is actually growing. At this point here, we add the beads in, and you can see a massive decrease in E. coli viability. So I heard yesterday that 4 log is the gold standard for reduction. So here's 6 log in 20 minutes. So that's quite nice. When we re-inoculate with E. coli every half hour, we get the same kill rate, so it's really, really reliable and reproducible. This data isn't made up, it's just the result of 5 replicates at each point and 6 sets of 10-fold dilutions. So the data is very, very good and very, very tight. It's quite outstanding, really. So you're adding 1 million E. coli per milliliter at the 8-litre scale, and we're powering this with a drill from a hardware shop. The drill speed hasn't been optimized, the beads haven't been optimized, the composition of the beads haven't been optimized, the size of the beads haven't been optimized. This is our first look-see, completely unoptimized. We can do 6 log in 20 minutes, which is, I think, is quite cool, but not cool enough. So we added 100 million E. coli per mil as well in the same system. So here about 10 to the 6 per mil. Here, half hour later, 10 to the 7, and here 10 to the 8. So we can get complete destruction within 20-25 minutes, even up at that scale. So if you just take this point here, so you've gone from 100,000 E. coli per mil to nothing in 5 minutes. So I count that as 1, 2, 3, 4, 5, 6 log reduction in 5 minutes, which shows you the sort of potential of this technology, and everything is unoptimized at the moment. So that was our phase 1 application to the Gates Foundation. So we were quite excited by this. So we immediately applied for phase 2 after 6 months of the project. We went a little too fast, I think, because we were working in isolation. The Seattle fair was great because it sort of really exposed us to the actual real problems of the field. And one thing that's come up is the helminth issue, which we were completely unaware of because we were just so ignorant of the field. But hopefully now through meetings like that, so yeah, we had to deal with the helminth issue. So Chris Buckley very kindly sent me a load of sort of protocols through on how to count helminth eggs and everything. So I went through those quite carefully and sort of researched helminth eggs. Turns out they're pretty indestructible. So I thought, well, we don't really need to destroy them. We could just bind them to something that floats and then just separate them away through the separation manifold. So we haven't. This is just one experiment, but here are human helminth eggs. Please don't tell me where I got them. Don't ask me where I got them, because I'm not allowed to tell you because the man who sourced them is very personal about it. But basically, if we have helminth eggs, we can expose them to our special new bead that we thought up might work, and we can bind it all the helminth eggs away. We can make alginate beads of various densities. We have various plastics that we use of various densities. We also have silica beads. So the helminth egg seems to bind quite nicely to silica. We can put silica beads inside the Vortex bioreactor. The beads are about 100 microns in size and cost about $65 per ton. They're really cheap. A ton of super buoyant beads takes up an awful lot of volume, and you don't need many of them to bind the egg. So this is actually quite an exciting time. So the next 6 months we'll be dealing with the helminth issue properly, and then we're looking for partners basically, because we are a very clean and ignorant and naive marine laboratory, and we need help getting this technology into the field for proper trials, because at the moment we're in complete isolation. So I'm looking for feedback and help from anyone who thinks they've got any contaminated water that they'd like to sort of try one of our systems at. And I'm pretty confident that no matter what size volume you've got, we can build you a rig to test it that'll sort it out. So that's where I'll end. I've got to acknowledge Simon, who's our microbiologist on the project, and Paul Rooks, the technician, Fabian, the poor Swiss technician who makes the beads, and Sohail, who's helped us out massively in the lab. Paul Goddard and Farid and Tarek and Santosh and Polo at PTL, who are our partners on this project. Stavrula and Neil at UCL did all the sort of modelling of the tubes, and Dan Drumheller is our sort of our angel in America who builds us stuff when we ask him. So, and I should have Paul Mason on here as well. I just realised he's not on there. There's so many Pauls on the project, it's quite easy to forget them. But he's